Okay, welcome back to another video. Here we have the test corrections for polynomial functions and rates of change quiz. I will say, do not watch this video until you've done it yourself, because you won't get as much out of it, and that is cheating. So I'm going to give you your chance, go do it yourself, because when I'm reviewing these, I have no way to hide the answers. So go do that. Anyways, starting off with this question. For the polynomial function g, the rate of change g is increasing for x is less than 2 and decreasing for x is greater than 2. Which of the following must be true? Okay, so polynomial function g, rate of change is increasing for x is less than 2. And remember, you may not have watched the last video, but we have an acronym, RAVE. It's our way of simplifying complex problems. So first we read and reread. So we're reading this again. Polynomial function, the rate of change is increasing and decreasing. So we're looking at concavity, right? Because increasing rate of change and decreasing rate of change has to do with concavity. Got it. So which of the following must be true? Alright, so let's draw this out. Actually, no, let's read the answer choices first, because that's the order. I mean, it doesn't really matter what order you do it in, but answer choices do help out. So graph of g has a minimum of at x equals 2, okay? Maximum x equals 2, point of inflection at x equals 2, concave down, concave up, concave down, concave up. Okay, so we're looking for, like I said, concavity or maximum and minimum. Let's draw this out. So we don't really need the coordinates because we're only just going around a central point. So we're going to do that. That's 2 right there. Congratulations. So if we look at this, rate of change is increasing when x is less than 2. So rate of change is increasing. No, that's not how that works. How would we do this? Like this. Because we're going faster and faster and faster and faster, right? And then rate of change is decreasing for x is greater than 2. So we're going fast, but then I don't really want to go fast anymore, right? So we get this kind of cubic function looking thing. Now, this right here, concave up. Rate of change is increasing, that's concave up. And also you can do the water test, oh, it can hold water or whatever. And then this is concave down, because rate of change is decreasing. Oh, it can't hold water. I don't like the water test because it doesn't cover edge cases very well. Like if you have a line like this, very, very bad example, but like a lot of these can't hold water even if they're concave up. Like this thing right here could be concave up. It just can't hold water. I don't know. I just don't like it. So we know that this side is concave up and this side is concave down. And we have no visible maximums or minimums here, so we can immediately eliminate A and B. The graph has a point of inflection x equals 2. These are both inflections, so that's true. Concave down for x is less than 2. Let's see, is that concave down? No, that's not. So it can't be that. Concave up for x is greater than 2. Not true. Concave up for x is less than 2? True. We got that. So that's correct. Next one. Polynomial function f is given by f of x equals x minus 4, 3x minus 1 squared. Which of the following descriptions of f is true? Okay. Let's read our answer choices. Is a polynomial degree of 2, leading coefficient of 3, degree of 2, leading coefficient of 9, degree of 3. Okay. Let's think about this, right? I'm going to take this and visualize it out in our little work area. Expand, I don't care. Okay. So this is our equation. Now to determine the degree in these sorts of equations, what we're going to do is we're going to count the number of x's. So we have 1x here, no exponent, right? So just by default that's a 1. So that's 1x in this expression right here. And then we have 3 x's, no, not 3 x's, we have 1x here because there's an exponent of 1, and then we have an exponent of 2 on the end, which means there's 2 x's. So it's a total of 3. So our degree for this entire polynomial is degree of 3. So now it can either be a leading coefficient of 3 or a leading coefficient of 9. Now it's really easy to say 3, because look, we got a 3 right there. But leading coefficient is when it's expanded. If we were to expand this, 3x minus 1 times 3x minus 1, I don't even have to do the rest of the math. I do this, immediately 9x squared. Leading coefficient is 9. We don't have to do the rest. We figure this out, and there's no way that this x is going to beat that. Because, again, it's just not an exponent. Like, this 9x squared wins, so this is the leading coefficient right here. And the degree of the entire polynomial is the amount of x's total. So that means we have a leading coefficient of 9, right? This one here tripped me up, because I did not read the question. So we're going to read the question here. Values of the polynomial function f for selected values of x are given on the table. Okay. So we're given a few values from a function, and we don't know the graph. We don't know the exact equation for it. That's fine. If all the zeros of the function f are given on the table, which of the following must be true? Now notice this. If all of the zeros of the function f are given on the table, this will be important. So let's read through our answer choices. Function f has local minimum, minimum, maximum, maximum. Okay, so we're looking for local minimums or maximums. That is what we're keeping in our brain, right? So let's draw this out. Let me bring this into our workspace here, like so. Let's draw this out. So we're starting really low, negative 36, and as we're going up, we get to 0, and then we get to 4, and we go back down to 0, and then we go up to 12, right? And remember, this is 0, and this is 0, so that we have our x-axis right here. Oopsies. Don't have to be precise. We have our point, point. Now, what's really easy to say, and what I did was maximum, right there. 3, 4. Let me switch colors. 3, 4, maximum, right there. Easy. Next question, right? But you have to read. If all the zeros of the function f are given on the table, and also you have to visualize, isn't this a local minimum as well? Well, how are these not both correct? Well, I'll tell you. And you might think it's really dumb, and it kind of is. So, no one said that it stopped here. It could just keep increasing and then come back down. You don't know that. This could be the maximum at some arbitrary point. You don't know. All you know is that there is a point here. If anything, the track between the points, let me just put a dot right here. Track between the points is entirely made up by us. This could be wrong, right? We could delete that, and the function could actually go like this. Right? Makes no sense, but again, we don't have the graph. It could be a piecewise function. We don't know. So what we could have is it goes like this, right? And you may be thinking, oh, well then, isn't this minimum not a minimum either, because you could just go past it? But all the zeros are given. We have all the zeros already. So that means if I were to go past this point, I'd have to come back up to go to 12, which is another 0, but they didn't include that 0. So that means that's wrong. You can't do that. So we can go past this, we could not go past this, doesn't matter. This is too inconsistent, we don't know if it's true or not. This, however, we know it's true, because this is the only 0. It doesn't go down and puncture back up, doesn't happen. Which means that it is a minimum, because you can't go below that without puncturing the x-axis again. And that makes us get the answer of f has a local minimum at 5, 0, because this is 5 and then this is 0. I didn't put it on a graphing plane, but I think you get it. The main difficulty is just behind reading comprehension skills, which I apparently am not good at. Let's look at this right here. The graph of the polynomial function g is shown. The function f is defined for x is greater than or equal to 0 and x is less than or equal to 3 is identical to the function g on that interval. How many local minima and local maxima does the function f have? Okay, so immediately what we're going to do is, these are kind of generic, they're just numbers. Like, we look at them, but they'll really come in handy later. It doesn't really tell us what to look for because we already know. So now, what I'm going to do is I'm actually going to use a fancy little tool here, right? And I'm going to crop this in the interval 0 to 3. 0 to 3. This is all we care about. I don't care about anything else. Now, what you'll notice here is it says local minima and local maxima. So the easy solution is to go 1, 2, done to 2. Right there, right? But what you actually want to do is you want to include these points, because they are minimums and maximums. They're local, but they are minimums and maximums, right? We go minimum, maximum, minimum, maximum. This is the max for this section right here. Does not go any higher. So you have to include those, which is really dumb, but there's no arrows. This is the entirety of the graph. There's no more. It doesn't go higher off screen. It doesn't go like that. No, that's it. That's all there is. So these are minimums and maximums. So that makes it 4. Because 1, 2, 3, 4. What I got wrong here was I just counted 1, 2, 3, 4, 5, and I just put it in. Did not take my time. Okay. Polynomial function is given. Ax, whatever. This is a standard cubic function, not cubic. Standard 4th degree polynomial, right? Where a is not equal to 0, so the highest degree is not equal to 0. And these are all constants. What is true? Well, let's think about this. What are the rules for graphing equations? Let's look at this, right? So if I were to graph an equation with a degree of 1, so just x, right? Looks like this. Let me go smaller. Looks like this. If I were to draw with degree of 2, x squared, it's going to look like this. If I draw 1x cubed, it's going to look like this. And then x to the 4 looks like a parabola with some brain damage, right? Looks like some booty cheeks. Now, of course, it can look like this, or like that, but like generally you'll just see it like that, right? So, did I draw that right? Okay, so we're going in, and then like that. Yeah, that's what it looks like. It's this right here, big W. So you'll notice a pattern here. Odd degrees have no maximum, no minimum. Even degrees have only a minimum or only a maximum. Because if we had this upside down, this would be maximum. But no more, because it just keeps going, right? Odd, infinite, infinite. Even, minimum, infinite, right? So if we're going to look at this, the reason they give us so little information is because it's a 4th degree, which means it's even, which means it doesn't have both. You can't have global maximum and global minimum if it's so open-ended like that. It does have a maximum or minimum because, as we can see right here, it does. It's even. We have all the information we need because it either has global maximum or global minimum, not both. And the reason we don't know if it's maximum or minimum is because a of x can be negative, and if a of x was negative, it would look more like this, right? Still an even function, just flipped around. That's why this is the answer. How many points of inflection does the graph of f have on the given portion of the graph? So this is the given portion. So we read our answer choices, just numbers, 1, 3, 4, 5. But we know it's not 2. Like, okay. This one, very straightforward. We are going to mark our extrema, every single extrema. Boom. And notice how I didn't mark these. And it's because there's no change. It's not a maximum, not a minimum. This just keeps going. Right? And between each of these extrema, I'm going to put a line. Those are points of inflection. Right? So 1, 2, 3. Now notice I didn't put one here, I didn't put one here, because this is just nothing changes. There's no inflection. It's just concave down, concave up. Same thing. No inflection. But here, here, and here, we change between. And like I said, the easiest way to find that is just mark your points, mark your extrema, and then put between, and you're good to go. Normally, the amount of extrema there are will be one more than the amount of points of inflection, but just check, just make sure, because if you're sloppy, you could get a lot wrong. And that is all for the test corrections for polynomial functions and rates of change. I will be covering the other two in the next videos. They should come out tonight as well. Just keep your eyes peeled for those. And that will be all. Have a good night, y'all. Make sure to keep in mind, where is it? Rave. Read and reread, answer choices, visualize, and when you're doing it, explain it to yourself. Explain your answer choice to yourself. The reason I haven't been doing that is because I'm explaining it to you, so I don't really have to do that. But if it's on a test, explain to yourself, justify to yourself, why am I choosing this? Why is this correct? It'll do a world of good, because teaching makes learning a lot easier. But I'm going to get to the next one right now. So, see ya.